Welcome, ladies and gentlemen. May I have your attention, please? Thank you. Let's get going and make sure we're comfortable integrating transcendental functions. Those are exponential, logarithmic, and trigonometric. Now we have all our rules. And so when we integrate, an indefinite integral, we always want to make sure that we're remembering plus c. We're dealing with an antiderivative function, right? We're finding an antiderivative function such that when differentiated produces the original integrand. And we developed our final rules so we know what tangent integrates to. We first broke it up as a quotient, sine over cosine, right? And then considered the connection between those two pieces. We saw that that sine on top was the derivative of that cosine function on bottom raised to the first, which authorized the use of the natural log rule. But we don't have to do that every time. Now, if this had just been tangent of x, we know it would have come from negative natural log of absolute value of cosine of x plus c. However, it wasn't, right? It wasn't just tangent of x, it was tangent of 3x. And so in accordance with the chain rule, when differentiating, we know we'd have to multiply by the derivative of the base. The derivative of that inner function, in this case, the angle. And so we have to multiply by a 3 when differentiating, and that 3 wasn't present in the integrand, so what must we include? Well, we better include a 1/3, to counteract the fact that there was no 3 out front, and then our angle is still going to be in the same, so I'm getting negative 1/3 natural log of cosine of 3x plus c. Raise your hand if you have the same. So do you have the same? Keep your hand up if you could write this in an alternate form. What else could this look at, particularly if it's multiple choice? Thanks, hands down. Riley E?
1/3 natural log of c.
Absolutely. This is equivalent to positive 1/3 natural log of absolute value of secant of 3x close bars plus c. And so both of these are equivalent forms for the correct answer. Awesome. What questions do you guys have about number 1? Then let's consider number 2. We also developed a rule for anti-differentiating secant of theta. In order to do that, we had to multiply by a clever 1. We multiplied by a clever 1 and then distributed to provide for the derivative of that quantity on the bottom to the first power, which again authorized the use of natural log. Once we did that, however, we can commit it to memory and not have to do it ever again. And so we're going to go ahead and jump right to the answer because I know you guys have already made your flashcards. You've already made your flashcards over last weekend and added to your little baggies so that when you're around town, out and about, right, you guys have your little Ziploc baggie with you so you can take it out and practice your antiderivative rules. Let's do it. We know that secant of theta is going to anti-differentiate to natural log of absolute value of secant theta plus tangent theta close bars plus c. Raise your hand if you had that. So natural log of and then absolute value bars of. Good, and we can just do that from memory. There's no derivative of the angle, so we don't have to include a constant in this case. All right, I'm going to box this. Either of those are correct. I'm going to box this. All right, so we already have a rule for the antiderivative of secant squared, right? What function differentiates to secant squared? What function differentiates to secant squared? Hayden? Absolutely, and so this must have come from a tangent function, right? A tangent function of an angle plus c. We also know that our angles don't change, and so we know that this must have come from the tangent of 2x, right, plus c. It's just that my inner angle, my inside angle was 2x, and so in accordance with the chain rule, when differentiating, this would spit out a times 2, right, times the derivative of the angle, and there wasn't one there, so we must provide 1/2. And so we'll have to put a 1/2 here to account for the absence of the 2 in my original integrand function. And so let's see, 1/2 tangent of 2x plus c, that would differentiate to 1/2 times tangent differentiate to secant squared with the angle 2x, and then times the 2. Oh, the 2 and the 1/2 would cancel out. Raise your hand if you had number 3 correct. Right? You have number 3 correct? You guys are rocking it. You're going to be all ready for today. I know it. All right. So I want you to go ahead and share with the class when I call on you indeterminate forms. And so let's go ahead and share our indeterminate quotients, and you can give me both indeterminate quotients. Kyle?
0/0, or infinity over 0, or infinity over infinity.
Good, thank you. So we've got, and that's plus or minus. So we've got 0/0 and infinity over infinity plus or minus. Those are our indeterminate quotients. Thank you. What's our indeterminate product? Our indeterminate product. Joel?
0 times infinity.
0 times infinity. Good. And we saw how, right? We saw how that if we have two quantities approaching 0, multiplied by a different quantity approaching infinity. This is indeterminate depending upon the rates of growth in each of these quantities, or I should say rates of shrinking, right? If this first quantity is shrinking to 0 more quickly than the second quantity is growing to infinity, it's going to win the tug of war and pull the overall value of the product down to 0. Versus if the second quantity is growing more quickly to infinity than the first one shrinking, it's going to win the tug of war and pull the overall value of the product towards infinity. Or is there some balancing point, some break-even point, right? Like a constant, 17/3, that the value of the expression or product approaches, depending upon what x value you're looking at. So that's where L'Hopital's rule comes into play. L'Hopital's rule authorizes us to get derivatives involved, so we can compare rates of change and see if we can evaluate the original limit. All right, what's our indeterminate difference? Our indeterminate difference. James?
Infinity minus infinity.
Infinity minus infinity, good. And we saw how, again, depending upon which one's ballooning towards infinity more quickly, the first one could win and pull it towards infinity, the second one could win and pull it towards negative infinity, or there could be some balancing point. And lastly, our indeterminate powers. These were the trickiest. What was one indeterminate power? Tyler?
1 to the infinity.
1 to the infinity. Remember, this isn't the number 1 multiplied by itself, all right, an infinite number of times. That would just be 1, of course. It's because it's a limit. If this quantity is approaching 1, the base in that power is approaching 1 from the left-hand side, that number is like 0.9, 0.99. As we multiply a quantity less than 1 by itself repeatedly, that's going to shrink towards 0. 0.9 times 0.9 is 0.81. Times 0.9 is 0.729, and so on and so forth, so it's getting smaller, versus if the base is approaching 1 from the right-hand side, and that's numbers like 1.1, 1.01. If we multiply a quantity larger than 1 by itself over and over again, that's going to balloon towards infinity. So, right, what's going on here? It's indeterminate. What's a different indeterminate power? A different indeterminate power. Get ready. Annika.
0 to the 0.
0 to the 0. Good. 0 to the 0 is indeterminate. The base in this power is trying to bring the overall value of the power towards 0. The exponent in the power is trying to bring the overall value of the power to 1. Who wins? We don't know. It's indeterminate. And what's the final indeterminate form? Right? The final indeterminate form? Kobe?
Infinity to the 0.
Infinity to the 0. Good. Thank you. Again, for a similar reason, this time the base of the power is trying to bring the overall value of the power to infinity. The exponent in this power is trying to bring the overall value of the power towards 1, right? Who's going to win? We don't know. It's indeterminate. Okay, so we saw how our logarithmic, right, our logarithmic differentiation allowed us to handle the differentiation of a hybrid function, which is neither exponential function nor power function. There are x's in both the base and the exponent, right? Well, we used a technique that was similar. We go ahead and call this original limit expression that resulted in an indeterminate power. We called that y, and then we took the natural log of both sides so that we could bring down that exponent using properties and again rearrange it to make it look like one of the 2 forms that authorize the use of L'Hopital. So while all of these 7 forms are indeterminate, only those quotients authorize the use of L'Hopital. Awesome. All right, what questions do you guys have about our indeterminate forms? So let's go ahead and take care of our OTL number 5. There is no graph on the back of the half sheet, so you don't have to turn the half sheet in, but I would ask that you staple multiple pages together, and it seems like you guys did a great job starting the stapler during Bellwork. Thanks for sending that around so you guys will be ready to go. Please give yourself credit for those that you complete out of 31. Divide, enter, multiply by 2, and let's box that infinite campus score nice and large on top. Round it to the nearest half point. Make sure you're boxing that infinite campus score, so it's easy to record these and keep your infinite campus grades up to date. Again, name, first and last, 1A and number 5 clearly labeled. Please pass from the back to the front. Front rowers, make sure they're facing the same direction. I appreciate your help. And then we can get going with our discussion today. Everybody good with number 5? Cool. So today we're going to go ahead and continue our integration with transcendental functions, and we're going to consider special powers of trig functions. The key here, right? The key here is understanding the relationship between multiple pieces in my integrand function. And so for that, we're considering the chain rule, right? The chain rule as a strategy for differentiating. Knowing the chain rule well for differentiating is going to allow us to integrate well now when we're considering these special powers. So everybody in your note sheet, let's go ahead and find the indefinite integral of sine of 3x all to the 7th times cosine of 3x. There's two distinct pieces here in my integrand function. What we need to decide is what's the overall function, right? What's the overall function or rule that we might be using when integrating? And then which part is acting as the derivative of the other part. So go ahead and tell your partner which part of this integrand function, right, is acting as the derivative of the other or a portion thereof. And be ready to share with the class. Which part is the derivative of which, I guess? Okay. Still going? Getting hungry. Enough talk. Now let's eat. So who's the derivative of whom, right? Or a portion thereof. So what's the relationship here? Megan and Sophia?
Cosine is the derivative of sine of x.
Absolutely. And so if cosine of x is there acting as the derivative of sine, right? Sine of 3x all to the 7th, then we'll be authorized to utilize the power rule because the derivative of the base is present. In accordance with the chain rule, when differentiating a power function, we do exponent times the base times the derivative of the base. And so if we're considering this as an overall power function, which I heard several of you talking about, I'm not going to make that. If we're considering this overall as a power function, right, I need to make sure I provide for the derivative of the base in accordance with the chain rule. The derivative of sine 3x is almost cosine 3x, right? What else do we need here? Grace V?
We have 3 cosine 3x.
Absolutely. And so if we had a 3 cosine 3x dx, then we know that this would come straight from a power rule. A power rule where we add 1 to the exponent, right? Add 1 to the exponent and then divide by the new exponent. So if we had that 3 in front, this would have come directly from the sine of 3x all to the 8, right? Plus c divided by 8. So I add 1 to the exponent of my power function and divide by the new exponent. But I didn't have that 3 there. So what must we do to account for that? Well, because we didn't have that 3, we could cancel out with a 1/3, provide a 1/3. Also, we can get our final answer. It looks like I'm getting 24th, 1/24th as my constant here. So it looks like I get 1/24th sine to the 8th of 3x. That, remember, that means sine of 3x all to the 8th and then plus c. Does that make sense? So that's not really anything new, bless you, right? That's not really anything new, but we're going to practice discerning the connection between multiple pieces in the same integral. That's what we're after today. All right, now consider the sine of 2x, cosine of 6, 2x inside, right? Go ahead and decide the connection between, and go ahead and complete this one with your partner. So this is similar, a little bit different, but similar. Go ahead and complete this integration and be ready to share with the class. And I want you to do it with your partner. So go ahead and decide.
Yeah.
Okay, what did you guys get? So what did you guys get? Riley and Brandon?
We got -1/14 times cosine to the 7th of 2x plus c.
Raise your hand if you have the same as Brandon and Riley. So negative 1/14, negative 1/14 cosine to the 7th of 2x. Good job, plus c. Way to go, you guys. And so it looks like this sine of 2x, right, dx, is acting as the derivative of the base of my power function, cosine of 2x, except we still need 2, right? We still need a 2, and we need a negative. And so if we had a 2 and a negative, then we would have had our derivative of the base present. We could go straight to cosine to the 7th of 2x all over 7. But we didn't, so we needed to multiply by 1/2 and a negative, right? And a negative. So there's our negative. There's our 1/2. Dividing by the new exponent 7. 2 times 7 on the bottom is 14. Way to go, you guys. That's awesome. Okay. So we've handled integrands where we have two parts, right? And we can discern which part is acting as the derivative of the other, particularly with power functions. That's not so bad. What if we had a little less clear, right? What about secant squared w, tangent squared w, and integrating that with respect to w? Now our exponents are equal, right? Our exponents are equal. Go ahead and decide with your partner which is the derivative of which. Right? Which portion of the integrand is the derivative of the other, or a portion thereof?
I'm pretty sure it's
Oh, that's the derivative.
So even exponents, is this possible, right? The exponents are the same. How could one possibly be the derivative of the other? Well, which portion is the derivative of which? So which portion is the derivative of which? Courtney and Kobe?
secant is the derivative.
Secant squared is the derivative of tangent to the first. And so overall, right? Overall, if we're thinking of this as if we're thinking of that as my main power function, right? Tangent of w all squared, then we need the derivative of this base, tangent of w, in order to use the power rule in integrating. And the derivative of that base is the secant squared w dw. Do we need to include any constants? Any 1/2? Right? Any negatives? No, the derivative of tangent w is the secant squared w. So we'll go ahead and add 1 to the exponent, divide by the new exponent. So we will get a constant 1/3, but that comes from the power rule. It doesn't come from providing for the derivative of the angle or the derivative of the base. Awesome. So we can go right to our answer, you guys. It looks like this becomes 1/3 tangent cubed w plus c. Awesome. Raise your hand if you already had that before we did it. Anybody already have that down? So you recognize that ahead. It's good. So now let's go ahead and step away. Well, I don't want to say step away from the power rule, right? There I am giving too much away. What's the relationship between these two pieces? So we've got a little bit different looking integrand here. Go ahead and decide with your partner. What's the connection now between these pieces, and how could we integrate? And if you're able, right, go ahead and get an answer. If you're willing to share.
Because I know that the derivative of
Oh. Okay, ladies and gentlemen, let's come together let's come together and see what an antiderivative for that integrand function is. Again, there's a relationship between the two pieces, and it looks like that radical x on bottom, right? I heard someone saying hop the line and change the sign. It's there acting as part of the derivative of the angle, that root x. And so if I'm thinking of this overall as just a trig function rule, right? I know that an antiderivative for sine of theta would be opposite of cosine of theta, right? So, but it wasn't just theta, it was the square root of x. And so if I'm thinking about this as being my angle, right? If I'm thinking about the root x as being my angle, I know the derivative of the square root of x is the same as the derivative of x to the 1/2. If I were to differentiate this, and again, I'm just kind of thinking aloud, so this isn't necessarily the problem. I'm sort of thinking out loud. I'm thinking the derivative of that angle x to the 1/2 is really 1/2 x to the negative 1/2. And if I rewrote that with radicals and hop the line and change the sign, this would become 1/2 radical x. And so as I think aloud, I see that this radical x on bottom is here acting as part of the derivative of that angle, right? This angle in my original trig function. Except I'm missing something. I'm missing that 2 on the bottom. If I had a 2 on the bottom, I'd be all ready to go to negative cosine of root x plus c. Did I have a 2 on bottom? No, and so I need to account for that by multiplying by a 2 on top. And so I'll go ahead and multiply by a 2. In my integrand function, I'll get negative from sine versus cosine. 2 to counteract for the absence of the 2 on bottom. Cosine of original angle plus c. Raise your hand if you had negative 2 cosine root x plus c already. Who had that already? You guys are killing it. So I want you to know that I made an extra integral practice worksheet that gets at a chain rule, right? It's the connection between these two. But there's still some tricks of the trade that we need to be able to handle. And so while we've been comfortable determining the relationship between multiple pieces in an integrand function, what happens if there's not really multiple pieces? I mean, secant squared w dw, did we just develop a rule for secant squared last class? Last class? What do you mean? Don't you mean last semester, right? Do we already have a rule for secant squared? Yeah. Is there any trick here? No. Antiderivative of secant squared would be tangent of angle plus c, because tangent differentiates secant squared. So there's nothing new or special here, other than a tremendous setup for the second one. Dun, 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 dun. How tremendous is that? What if it had been an antiderivative for tangent squared of w, right? Is that just secant of w plus c? No. What's the derivative of secant w with respect to w? Secant w tangent w, right? And so clearly we can't go backwards in the same way, right? And so what are we going to do? Well, we have an antiderivative for tangent, right? We have an antiderivative for tangent. Is this natural log? No. A natural log as an antiderivative is only possible for a rule if I have some quantity on the bottom to the first power. And even if I rewrote that tangent as sine over cosine, I still have that exponent of 2, right? And so this is not going to be a natural log rule either. And so what are some other tools that we have at our disposal? Right? What else could we do to try and find an antiderivative for this? Riley F. script?
We could set it equal to y and then take the natural log of both sides.
Oh, I hadn't considered that. If we called this original integrand, or just the tangent squared, just the tangent squared equal to y, and then so if we called the tangent squared the original integrand function y and took the natural log of both sides, let's think what that would do for us. We'd have natural log of tangent of w to the second, right? And we could now use log of a power to bring down the 2 in front and have 2 natural log of tangent, right? But do we have an antiderivative for natural log of tangent? No, we'd have to have the derivative of, if we're thinking power rule, we'd have to have the derivative of the natural log which is 1 over the quantity times the derivative of the quantity. And so while that's certainly a technique that's allowed us to get rid of exponents, or move them, I should say, move them around, our exponent here is just a constant. It's not a variable. So that's kind of a difference. We don't need to get a variable down out of the exponent. Here is just a regular constant as my exponent, a regular power function with base, my variable function in the base. And so I don't think that we'll need to take the natural log here. But as I'm sifting around through my algebraic tool bag, the duct tape and tattered worn, I've kicked around the common denominator, right? I've scooched those out of the side. We've now moved the logarithmic, right? Taking the log of both sides out of the way too. What's left? We've got a whole collection from pre-calc and FST/pre-calc of those trigonometric identities, right? If we could rewrite my integrand function, as the case has been throughout a lot of this unit, rewriting using algebra, in this case, rewriting using identities, perhaps we could write the integrand function in a form that we do recognize an antiderivative for. And so let's consider some identities that we could use. So tangent of squared, right? What identity includes those squares? Right? Which identities include the squares? Did I have to memorize these? Yeah, the Pythagorean. Anytime we're dealing with the squares, right, and the sums or differences, a squared plus b squared equals c squared, those are my Pythagorean identities, and we can rearrange those into a host of different forms. And so we're trying to find the one that has a tangent squared. And so if we think back to our Pythagorean identities, remember a squared plus b squared equals c squared. If we don't have those memorized, it's okay. It just comes from our Pythagorean theorem, where this would be the leg lengths in a right triangle, and this would be the hypotenuse length. In terms of the unit circle, my horizontal leg length is cosine of theta. The vertical leg length is sine of theta, and so if I let A be the vertical leg length, I could have sine squared theta plus, and if I let B be my horizontal leg length, right, in a right triangle, this could be cosine of theta quantity squared. I'll call it cosine squared theta for short, equals, what's the radius in the unit circle? 1, so 1 squared is 1. So here's my main Pythagorean identity. From this, I can generate, right, all the other forms. So I want the one that has tangent squared theta. And so what can I do to generate one that had tangent squared theta? Well, I could divide all of these terms, right, by cosine squared theta, just so that I get a tangent squared out of this. If I divided each, right, both sides, each term by cosine squared theta, then sine squared theta over cosine squared theta is equivalent to, there's my lucky dog, I wanted tangent squared theta, plus, what's cosine squared theta over cosine squared theta? 1 equals, and what's 1 over cosine squared theta equivalent to? Secant squared, by golly. And we can do this and generate another 6, right, Pythagorean identities. It's just that we wanted the one that included tangent squared theta. So I know that tangent squared theta plus 1 equals secant squared theta. Therefore, rearranging this, don't get John, right? I know that tangent squared theta is equivalent to what? Well, tangent squared theta then must equal secant squared theta minus 1. If we rearrange that to equal the integrand in question, we can make a simple direct substitution using a Pythagorean identity and replace my integrand, tangent squared w, with what?
Secant squared minus 1.
Yep, secant squared w minus 1. Let's go ahead and do that, guys. So let's rewrite this as the integral of quantity secant squared w we're dealing with in this particular secant squared w minus 1 dw. Oh, Arthur. I remember that. Arthur and DW. A classic show. I miss that. All right. So did that help us at all? We just traded out one power function for another. Helps us out immensely. We already know the antiderivative for secant squared w is tangent theta. Then we can go term by term in accordance with differentiating a sum or difference, right? We can break it up and consider the separate derivatives. So too with anti-differentiating. And so to find the indefinite integral, we can break it up term by term and anti-differentiate. So we're ready for the answer. Let's do it. Antiderivative for secant squared w is tangent of w straight up minus an antiderivative for 1 with respect to w is w, comma baby. And then we need a plus c. That was awesome. So what's been a recurring theme in Unit 6? rewrite, whether it's using algebra or now using trigonometric identities, if, right? We've tried all our tricks, and I still don't know an antiderivative rule for my integrand. Let's try rewriting it with algebra or identities or other properties that we have at our disposal. That's pretty sweet. Awesome. Gosh darn it. All right, so we're gonna. I finished making that practice worksheet for indefinite integral practice, and you're gonna have an opportunity to work on that. That will be part of your OTL number 6, and we'll add that to our half sheet. But first, we're going to consider our second content objective. The fundamental theorem of calculus part 2, right? Directly connected differentiation and antidifferentiation as inverse processes. That is, if we had an original function, call it g of x, given by an integral defined expression, I know the derivative of that function, g of x, is just simply equal to that integrand function, f of x, okay? However, we now could think of that integral defined function, right, as a function in its own right, that has values that could be determined by direct substitution. And so if we wanted to determine the value of g of negative 2, a particular x value, we could plug x equals negative 2 into my function definition everywhere I see an x and then evaluate it. I want you to think of this as an area accumulator function. We're going to start at this lower limit, at this case negative 2, and we're going to scan towards the upper limit, whether that's to the left or to the right, and accumulate area, such that area counted right above the x-axis is going to be a positive contribution to the value of now this definite integral. And any area accumulated beneath the x-axis is going to count as a negative contribution towards the value of that definite integral. However, if my input is negative 2, how far can I scan, right, from negative 2 up until my upper limit, negative 2? Well, I'm not going to be scanning at all. So how much area could be accumulated as I scan from negative 2 to negative 2? 0 units of area. And so if my upper limit is the same as my lower limit, then guaranteed this is a 0 or x-intercept of my original function g. So this equals 0 because I can't accumulate any area, right, between negative 2 and negative 2. Not so with g of 0. For g of 0, I will start at my lower limit, negative 2, and I will scan towards the upper limit, keeping in mind that may be to the left or may be to the right of my lower limit. But as I scan, I'm going to be accumulating area and interpreting this as this definite integral as, right, the number of units accumulated above minus the number of units accumulated below as I scan from left to right. So let's do it. As I scan from negative 2 up until x equals 0, how much area have I accumulated? Well, I've got 1 square unit, 2 square units, and then this is just a triangle, so I could do 1/2 base times height. 1/2 times 1 times 2 is just 1, so it looks like 1, 2, 3 units. So guess what? G of 0 is the definite integral from negative 2 to 0 of f of t, whose graph is shown, which is just an area problem. And that's why I get 1, 2, half of the 2 is 3. You guys get 3? You see that? So we can interpret this integral defined expression, this function, as an area accumulator. Start at your lower limit, scan towards the upper limit, and count up units. Let's do another. G of negative 5 says, plug in negative 5 for x, right? And evaluate the definite integral from negative 2 to negative 5 of my integrand function, f of t, whose graph is shown. So everybody, let's start at negative 2, and let's scan towards the upper limit. In this case, my upper limit, negative 5, is to the left of my lower limit. So I'm scanning from right to left, which means that, right, my normal interpretation of area accumulated above as a positive contributor is going to be backwards. Or shall I say bass-ackwards? That's fun, even for a Monday, right? It's a bass-ackwards interpretation now, because as I scan from right to left, now all my little delta x steps, right, are slightly negative, and so my widths of rectangles are negative, times my function values are still positive, gives me an overall negative value for area. Let's do it. So I've got 1, 2, 3, 4. That's supposed to be 5. That's supposed to be an x-intercept, and we'll count that as a half. So what do we think? 1, 2, 3, 4, 5 and a half. You guys good? 5 and a half. Let's do that. Negative 5.5. Why do we need a negative? Because you're scanning from right to left, and so any area above is going to be not a positive contribution now, but a negative. Good, thank you. So we need a negative there. Am I going to fit it? I think I can. I don't think I can. We want PDFable. So negative 5.5. Good, thank you guys. Nice catch. Okay. Let's go ahead and you do g of 3 now. So go ahead and do g of 3. We'll do same picture, same function. Okay, time to share. So as I scan from my lower limit, -2, up until my upper limit, +3, this looks like a normal interpretation of area accumulated from left to right. And it looks like this positive contribution is canceled out by the time we get to x equals 2 by an equal and opposite, right, negative contribution, which means that we've got 2 units remaining. So raise your hand if you had -2. Who had -2 for the value of g of 3? Awesome work, you guys. That's perfect. Great. All right, so far we've interpreted my original function g, which was integral defined, as an area accumulator, right? And evaluated the value of my function by considering definite integrals. That is the area in between my integrand function and the x-axis as I scan from left to right. Normal interpretation left to right, area above is positive, area below is negative. Opposite interpretation if I scan from lower limit towards the upper limit, but moving from right to left. Then the positive, the area above counts as a negative contribution, and then area below counts as a positive contribution. Now let's get derivatives involved. And so the fundamental theorem of calculus part 2 said that if g is an integral defined expression, right, from a constant up until my independent variable, then g prime of x, the derivative of this integral defined expression, differentiating that integral undoes it. Just like multiplication undoes division, or subtraction undoes addition. Differentiation and integration are inverse processes. So what's the derivative of this integral? Well, it undoes it, and you're left with the integrand function, with the important difference that now my upper limit, my independent variable, is right in my integrand function. So what does this mean? The fundamental theorem of calculus means, part 2, means that if g is given by the integral from any constant up until my independent variable x, then g prime of x is given by what? F of x. That's it. Which means that if I want to evaluate g prime of 3, this is equivalent to f of 3. What? G prime of x is equal to f of x, so g prime of 3 is equal to f of 3. So as we look at f of 3, that's simply the value of my function f whose graph is shown when x equals 3. Can we do that? How come it's not undefined? Look at that corner of cusp. Isn't that undefined? Brandon?
We're looking at the continuity, not the differentiability of the function.
Agreed. We're looking at the function values of the shown function f. We're not looking at the differentiability of the shown function f. We're simply looking at the function value f of 3. And the function value returned is -2, but for a very different reason. This is a different -2. -2. Yeah. Can we go a step further? You bet your boots. We can evaluate g double prime of 0 now, right? If we know what g prime of is, then don't we know what g double prime is? Certainly. If g prime of x equals f of x, then let's go one step further. G double prime of x must be given by what? F prime of x. Stepping down one more rung on our proverbial calculus ladder. Oh, love math. I love this class. All right, so g double prime of 0, that is the same as f prime of 0. So f prime of 0 would be the derivative of the shown graph at x equals 0. So can we find that? Certainly. We're looking for the derivative of this graph f at x equals 0. And so is that equal 0? No, right? It's the slope of the line segment, the slope of the curve, when x equals 0 of the shown graph in red. Can we calculate that? Yeah, if we have a line segment, I can just count out rise over run. Looks like down 4 over 2. So that would be what? For the third time in a row, negative 2, but now for a very different reason again. So these are all negative 2, but for different reasons. That's pretty sweet. We'll see more with the fundamental theorem of calculus, right? Interpreted as an area accumulator and graphically applied next class, and then again in Unit 10. Okay, so we've got that to look forward to. I'm excited about ourselves. So what's this? Well, this is two fat asterisks right here to remind us that we need to add, mainly so I can say that, mainly so that we remember to add this, right? We add this to our OTL number 6, and so I figured those out without having this. Everybody please include our integrals practice worksheet. Our integrals practice worksheet is the one-page two-sided that you picked up on your way in. And I have the answer key hyperlinked on Moodle, but I left it on the left-hand side of the block. And so I want you to go ahead and work on that first. And you may work with your partner. And so we've structured in some work time because last time some students struggled with our antiderivatives and our integrals. And so I wanted to make sure that you had more practice. That's why I made this extra integrals practice worksheet. I want you to work on that first and then continue with the bookwork. You got a nice chunk of time. Thank you in advance for using Creative Calculus. I'm going to go ahead and pause and save the recording.